So again class, last time we discussed simple harmonic motion in horizontal na case niya, no? Simple harmonic motion in a simple harmonic oscillator in horizontal motion. So now what if we have this effect of what if nakoy oscillator, nakoy mass, tapos attach mo sa spring, but butahan mo siya not horizontally but vertically. Okay, so we have excuse to share screen whiteboard. Open na jam. Creating send. Okay, so last time we have this. Last discussion, we have this system. Okay, mass M, and then we attach him just a spring with some spring constant K, and then the equation of motion, which we solved this one last time. The equation of motion of this is equal to this one, right? Okay, x dot plus K over M x equal to 0. So this will be the equation of motion, and from this equation of motion na solve na to nga si solution x of t, the solution, it's either a cosine or a sine. Okay, so it's either a cosine or a sine. So ako na lang duhaon, no? It's either this cosine omega t or plus sine omega t. Okay, so mamili lang ka sa duha, no? Kung for example, if depende sa yung initial condition, mogamit ka cosine, mogamit ka og sine. Depende sa yung initial condition kung sa ka mogamit og cosine and kung sa ka mogamit og sine. Okay, so that's for harmonic oscillator in 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 horizontal motion. Okay, so next is what if again. What if imo siyang butang, what if there is an effect of gravity. Okay, there is an effect of gravity uh, sa ato ang harmonic oscillator. Okay, so we have effect. Take note, gravity is a constant external force, no? uh, effect effect of a constant external force on a harmonic oscillator. Okay, so question is, parehas ra ba siya og equation of motion? Unsay kalahian, unsay madungag or unsay diferensya kung imuha siyang the figure looks like this. Is tanaw na to ang figure, ha. So unsay madungag or unsay diferensya or parehas ra ba iyang equation of motion kung ipatindog nimo or ipahigda nimo ang imong harmonic oscillator, no? Tanaw na to sa analytical kani. Ang iyang figure is this. You attach a spring. oops. Ito. Okay, kanina. The vertical case for the harmonic oscillator. So, okay. So, ingani siya og system. Okay? So, nakoy spring, butangan nimo, gi-attach nimo ang mass sa imong spring, pero in the presence of gravity na, no? So, kung naay gravity, take note this constant external force here, okay? The constant external force here is the gravitational force. Okay? Take note, ha? The gravitational force. And we know that gravitational force, the magnitude of the gravitational force is equal to m times g. That's why natay makita diri nga mg sa ato ang equation in our system. Okay? So, again, ang goal is to calculate the equation of motion o i-compare nato ang atong harmonic oscillator, ang ato ang equation of motion in for vertical case and for horizontal case. Okay, so tanaw na to, no? Ah, take note, kung magbutang og mass, what will happen kung spring lang siya, kung spring lang siya, okay, kung ako spring lang, okay, so dira ay ang equilibrium position, no? As you can see, if you draw the uh, the equilibrium position, na diri imong equilibrium position. Now, when you put some mass in your spring, okay? I-attach mo ang mass sa spring. What will happen is mo stretch sa gamay. Sakto? Idako na ito. Pero mo stretch ang imong spring, kay mo stretch sa gamay because of this mass M. Sakto? Mo man ito makita ka sa kala, no? So, the equilibrium position now, igo ra nimo gibutang ha, wala nimo gi-stretch, wala nimo gidungagan og force, nga i-stretch mo ang spring. Igo lang nimo gibutang uh, ang imong mass, okay? So this is your new equilibrium ang position now because of this mass M, okay? So mo ni tabulary, no? As you can see na ako'y duha ka measurements, kani, okay? Kani yang i-consider una, and ang kaduha nga measurement is katong base sa iyahang new equilibrium position. So what do you mean by new equilibrium position? Katong once gi-attach na nimo ang mass sa spring, mo stretch sa gamay, okay? And then that the new distance na, the new x now is we call that one as new equilibrium position. So somewhat kani is gadepende lang siya ang kani no, kani gadepende lang siya sa imuhang uh, katong equilibrium position xe nga katong wala pa nimo gibutang ang mass, okay? Kani pa, no, kani pa di base sa equilibrium position nga old nga equilibrium position, and ang kaning ikaduha nga measurement is gabase ka or gabase ta sa ato ang new equilibrium position, okay? Gabase ta sa ato ang new equilibrium position, okay? So to solve this one, to solve the equation of motion, if you write the force, if I write the force here, sa kani nga term, if I write the force here, your force is equal to minus k times some x, dako nga x ni siya, no? Irisan ako nga siya, sa nakalimutan. Dire na ako ibutang sa next page na lang, no? Ibutang ako sa next page. Excuse. Okay, and then sulat na to, ha. Base sa katong base ta sa old equilibrium niya nga position, makakuha ta og expression sa atong force. Kani base ta ani, no? Mag-base ta ani. If you base our calculation sa kana nga base from the old equilibrium position, makakuha og force equal to this. F is equal to minus k times dagkong ni nga x, ha, dagkong nga x, kani nga x minus the old equilibrium position xe plus the gravitational force. Sakto ba? Kaya ang force lang na diri is the Hooke's law, the restoring force, which is equal to kx, and the constant external force, which is our gravitational force, okay? So which is our gravitational force equal to mg, okay? So based from that, once natin force, makuha na ito ang equation of motion mo, ano? Pero we will try to solve this one in different way. What if i-solve na ko siya in terms of the new equilibrium position, okay? So in terms of this kaning mga terms dari, okay? In terms of the new equilibrium position, take note this prime, okay? I let this x e prime, dagko ni siya, no? X e prime as our new equilibrium position. Take note, equilibrium position, new equilibrium position is katong gibutang na nimo ang ang mass sa spring. Okay? Now, so the XE here, okay, the new equilibrium position can be written equal to this, right? Na ko XE plus mass times gravity. Sakto ba? Yeah, sakto. In the presence of gravity, imong weight, no? Ang weight sa imong mass may ma-add nimo para makuha nimo ang new equilibrium position. Ana pay mg over k, sorry. Nakoy mg over k. Sakto? The distance nga the new equilibrium position x prime can be expressed in terms of the old equilibrium position plus the mg over k. Okay? The weight over the some spring constant k. And from this, so if again, iset na nako ang this is based from the new equilibrium position, okay? Uh, at that point, your force there is equal to 0. Sakto ba? Kay wala man siya na the summation of force is equal to 0. The summation of force the summation of force asa pa, no? So therefore, based from this, okay? Based from this, I can solve for f equal to this. Na ko minus k xe minus xe plus m times g. Sakto ba? I can solve for the force in terms of this new equilibrium position equal to this. F is equal to minus k xe prime minus the old equilibrium position plus the mg. And from this, setting f equals 0 at new equilibrium position, okay? Equilibrium position, the summation of force there is equal to 0. So therefore, f must be equal to 0 there. So therefore, if we set f equals 0, so mabilin is na ko k dagko kani xe plus m times g. And based from this, masolve na ko ang xe, right? I can solve now for xe. Xe now, xe equal to xe plus mg over k. Okay? Mg over k. Okay? So, muna ito ang kanino? Kani siya? Which is this one, no? Equilibrium position u is equal to the old equilibrium plus mg over k. Now, as you can see from the figure, kaning gamay nga x, okay? Take note ha, kaning gamay nga x, which is muna among stretch na distance based from the new equilibrium position can be written as using kulantaw nimo si x kay masolve nimo using this, no? Ay, tanaw na to throw. Oy, wala na. Oops. Wait sa. Kulantaw na to sa figure, no? Kulantaw nimo sa figure si x nga gamay. Okay, si x nga gamay is just equal to x nga dako. Kani minus nimo aning equilibrium position. Sakto ba? So the x nga gamay is equal to dako kay nga x minus the new equilibrium position. And we know equilibrium position nga xe prime, no? Si xe prime, so x now is equal to dako nga x minus the xe which is equal to the old equilibrium position plus mg over k. Okay? And if you do the math, you have x equal to kung nga x minus xe minus mg over k. And based from this, makuha na ko ang difference ni x minus xe equal to dako nga x, agamay nga x plus mg over k. And at this, we actually relate the measurements, kani? We actually relate the measurements based from the old equilibrium position and this kaning new equilibrium position. And I know that our force is given by this equation here. Okay, so if you substitute the x minus xe here, you will get then the force. Okay, then the force F, which is equal to so ito minus k in terms sa tong old, no, x minus xe plus mg is equal to this, no, nakoy minus k so itong x minus xe na to, x minus xe is x plus mg over k, nakoy gamay nga x plus mg over k plus mg. Substitute the k, you will have kx minus mg plus mg. You can cancel out this. You will get f is equal to minus kx. And notice this is just the same na force na differential equation sa tatong harmonic oscillator in horizontal case. Sakto? So based from that, makuha nato ang equation of motion. The equation of motion will be equal to this. Same ra gyapon sila og equation of motion, sakto? Kx equal to 0. Again, this x here nga gamay, this is based from the measurements along based from the measurement on the new equilibrium position. Okay? So, as you can see in horizontal and vertical case, we can conclude now that the equation of motion is the same, but there will be shifting of displacement. Okay? Ni shift ng gamay imong displacement, no, kay ni stretch ang kaning x is based from the new equilibrium position man, no. So naay shifting of displacement, naay shifting of position. So there will be shifting of position, but take note the equation of motion is actually the same, no? Same ra sila og equation of motion. So we can conclude. We have conclusion. Dili na ako bisa. This is for any external force, okay? For any external force, for any external force, constant. Importante ang constant, no? For any external constant force, gravity, like gravity, no? Constant force, say mg, bisa konsa, no? Basta constant lang siya. Applied to a harmonic oscillator. Take note ha, i-emphasize na ako ang constant because later, kung maabot ka o damping na natay force harmonic oscillator, then natay add nga term nga dili constant. Depende siya sa velocity baka, depende siya sa position baka, and so on. But here, the external force na atong gi-add is only a constant force. Okay? So if any external force applied to a harmonic oscillator merely shift, so nasa diferensya, ni shift lang iyahang equilibrium position. So there is shifting of equilibrium position, but take note the equation of motion remains unchanged. Okay? Remains unchanged if we measure the displacement based from the new equilibrium points. Okay? So muna to na conclude, no? Take note, vertical pa man, mapa-vertical, mapa-horizontal, same equation of motion as long as your force nga gi-apply, nga gidungag, no? As long as the force nga imong gidungag is a constant force. Okay? Same equation of motion nga makuha, but there will be shifting of displacement. Okay? There will be shifting of displacement. Say for example, okay, my example there is kanino? Okay, can example 3.2.1. Okay. Yeah. Hello? Okay pa mudra? Do you have any question?
None, sir.
Wala, sir.
Okay, sige. Padayon ta, no? Padayon ta. Okay, say for example this one. So, na ako spring supported a block of mass in a vertical motion. So, same setup atong gi-solve na, no? The spring is found to stretch by an amount of D1. So, first, na ako spring. So, if you draw this one, na ako spring, no? Okay? Yan ala sa. Okay, muna ahang um, old equilibrium position. Now, if you put mass, if you put mass M, what will happen is there will be a stretch distance if you put mass M. So, ga-stretch siya gamay at the distance of yan siya kay distance niya is D1. Okay? So, muna siya, no? The spring is found to stretch by an amount of D1 over its unstretched length. Okay? Kana siya, gibutang pa nimo ang mass. Igo rin nimo gibutang ang mass. May stretch siya gamay at some distance D1. Now, ang imong gibuhat na pod is, so nana ko D1 no, nga distance no from the unstretched length. If the block, excuse, if the block is furthermore pulled downward at a distance of D2, so what will happen is, na-exert ka of force, okay, another ang mass, so imo na siyang imo na siyang sana? Gibira, no? Imo siyang gibira, then you pull it downward at a distance of D2. So therefore, excuse, so na ko dito na nga position, position from the equilibrium. And then what will happen is, gibira nimo no, gipull nimo some distance dito. Then ang buhat nimo is gibuhian nimo siya. So what will happen is, this will go there and then back sa dire. So you will get a simple harmonic motion. Okay? You will get a simple harmonic motion. So the graph will be, the graph of your mass will be, it looks like this. Okay? So question is, the graph will look like this one. Oops. Tingnan na sa forma ng layer, no? Okay? At some amplitude of D2 na siya, no? At some amplitude of D2. Okay. Question is, what will be the resulting motion? Meaning the resulting motion is you will get the position or the displacement of your mass, the velocity of your mass, and the acceleration of your mass. That's for letter A. Part B is what will be the velocity of the block when it passes back upward through the equilibrium position, and next is the acceleration at the top of its oscillatory motion. So before we solve for the velocity and acceleration at the top or katong when x equals 0 through the equilibrium position, solve sa nato unsa ang ato ang resulting motion. Again, same equation of motion. Okay, solution, same equation of motion. Mx double dot plus kx equal to 0, and you will get the solution of this one is, it's either a cosine, okay, omega t. Take note your omega here. Omega is equal to square root of k over m. It's either a cosine or a sine. Pero makita mo na to daan, no? Dari palang daan sa problem. You pull downward a distance d2 from equilibrium position and release. So, unsay meaning ana? Meaning is ga-start ka sa pinakataas nga distance, okay? Ga-start ka sa ihang maximum nga distance. Ang imong motion ga-start sa ihang maximum nga distance d2, no? Gi-release man nimo sa atong nga time. So, as you can see the graph is at time equals 0, at time equals 0, your displacement is maximum. So, muna ang point there, no? So, kanus ang maximum displacement at time equals 0, it is when your displacement is expressed in terms of cosine. Sakto ba? Cosine, no? Kung lantanin mo at time equals 0, kung natin ang mga initial conditions, no? Initial conditions at time equals 0. So, kabalo ko nga cosine ako magamit ani, no? Pero tanaw na to kung cosine ba yun, no? At time equals 0, your x is equal to d2. Sakto? Yes. Your x is equal to d2. And then your velocity, I call this one as v naught. This is equal also to 0. Okay? It means that your x dot, first x dot is equal to 0. Kay wala man sa naglihok initially, no? Gipull raman nimo, gipull nimo. Then pag-release nimo, the initial velocity is ang initial niya velocity is 0. Okay? As you can see, at time equals 0, so nakoy based from this nakoy x at time equals 0 is equal to d2. Sakto? Nakoy a cosine of omega times 0 plus b sine of omega times 0. So, ang mahitabo, take note, the position at time equals 0 is d2. So, I have d2 equal to cosine of 0 is 1. So, nakoy a cosine of 0 plus b sine of 0. And we know sine of 0 is 0. So, and cosine of 0 is 1. So, therefore, the constant a, we call this one as amplitude, is equal to d2. Okay? So, nanakoy nakuha nga a equal to d2. And, ma-reduce na nimo, the solution will be reduced. The solution will be reduced to this. X of t equal to a cosine of omega times t. Wala na ito yung sign, no? So, muna akong gingon ganyan na, no? Dili pa lang daan sa problem, kabalo na kung nga cosine akong gamiton. But anyways, kung di ka kabalo, nga cosine ka mo gamit, lantawan mo ang yung initial nga mga conditions. Okay? Initial means your time, when time is equal to 0, your position is maximum, your velocity is equal to 0. Anyways, so na ko a cosine, kabalo na ko sa a, no? A is d2 cosine of omega times t. Okay? Then, next question is, what will be the the omega? Okay? So, what will be the omega? Dili man given sa omega, no? Okay, wala mong k, sakto? Wala may k sa ako ang spring. Dili given si k. So, kung no? Since dili given si k, so we cannot use this equation here. So, saan ako pag-solve si omega? Dali lang, no? Napako isa ka initial condition. At time equals 0. Excuse. At time equals 0. At time equals 0. Your x dot is equal to 0. Sakto? Your x dot is equal to 0. Now, if you derive this equation, recall that x is equal to a cosine omega t plus b sine omega t. Okay? If you derive this one, x dot with respect to time, this will be equal to negative a sine of omega t plus b cosine of omega t. Sakto? Tama ba? Yeah. And then at time equals 0, x dot is equal to 0. So therefore, at time equals 0, x time equal to 0, x dot sorry, the velocity, okay, the velocity at time equals 0 is na ko minus a sine of omega times 0, which is 0. Ay 0 na diretso, no? Sine of 0 plus b cosine of 0, cosine of 0, yeah, is equal to 0. And in this case, makita nato nga si b, diri pa rin ito makita, no? Makita nato this one is 0, b cosine of 0 is 1, so therefore b is equal to 0. Okay? So then, yeah, again, ma-reduce na nimo siya into this, right? Nako a cosine of uh, ito. Ma-reduce na ko siya sa a x t equal to a cosine d2 cosine of omega t. Okay? Aha. Si omega is equal to this. Omega can be expressed, can be expressed equal to k over m. Okay? But we don't know yet k, right? We don't know yet k, but we can solve for k. Take note, at new equilibrium position, you have this f. Take note, you have this one, f is equal to kaning una niya condition, no? Ang iyang una nga condition is the spring is found to stretch by an amount of d1. So therefore, you can write your f there equal to minus k d1 plus the weight of your mass m, which is equal to m times g. Okay? Tama? Ako'y elastic nga force, the Hooke's law, plus the restoring force plus the weight of your mass equal to mg. And from that, nasolve na ko si k there. Okay? Nasolve na ko si k there. At new equilibrium position, your f is equal to 0, which is equal to minus k d1 plus m times g. Sakto? This is at equilibrium, new equilibrium position, no? At new equilibrium position, the summation of f there at that point is equal to 0. So we have minus k d1 plus mg. So therefore, masolve na ko si k. K is equal to m g over d1. Aha, ano ko k? So masolve na ko si omega. Omega is just equal to mg over d1 times m. So therefore, omega is equal to g over d1. Aha. So I have now this displacement. So makuha na ako sa displacement. Displacement then, therefore, or thus, the displacement as a function of time, the displacement as a function of time, is equal to this. X as a function of time equal to the amplitude d2 cosine of omega, which is equal to ito? Omega kay g over d1. Okay, g over d1. This is your omega g over d1 times some time t. And based from this, masolve na ko si velocity. So this will be my displacement or my position. So this will be my displacement. How about my velocity? Velocity, you just have to derive this function x as a function of time. So kung i-derive na ko na cosine, derivative of cosine is negative sine. So I have negative d2 omega, which is g over d1, sine of omega g over d1 times t. How about my acceleration? Acceleration, you just have to take the double derivative of your x as a function of time. So you have minus d2 square root of g over d1 square, that will be equal to g over d1. Okay? Matanggal ang square root, no? Omega square is g over d1 lang. Cosine of square root of g over d1 times t. Okay? So this will be the resulting motion okay, of the system. Okay, so this will be the resulting motion of the system. I think dirata taman. Thank you.